Okay, well, welcome to section 7. We are going to start looking at experimental design and ANOVA. The first one we want to look at is a matched pair design. Matched pair is used when we want to remove variability by using the exact same person or timing or whatever it is, and using two different methods. So, for example, let's think about it this way: when we want to see which method of processing invoices is better, we would use one person and then offer them two different methods, or at least use both of those methods to determine which one is faster or better or more accurate. So the same person uses two different methods. In essence, we're matching, right, those methods to one person, and we're removing the variability that we would have between individuals. Okay. So here's a quick example. A Chicago firm has documents that must be quickly distributed to a district office throughout the U.S. The firm must decide between two delivery services, UPX and Intex, to transport their documents. In testing the delivery times of the two services, the firm sent two reports to a random sample of its district offices, with one report carried by each of the different services. Does the data on the next slide indicate that there's a difference in the average delivery times for the two services using a 0.05 level of significance? So let's take a look at the data. And again, this is a matched sample because we are matching the city of Seattle, and they'll have two different situations there where they will look at the times for each of the services. If we were to have Seattle and Cincinnati and you know a bunch of different cities, not just these 10 or so listed here, but we use different ones for UPX and a different one for Intex. In that case, it wouldn't be matched pair. We'd have variability that would happen within those cities that we'd have to somehow account for. But within matched pair, we're able to get a good idea because we've matched them on the city. Okay. Within matched pair, we are only concerned about the differences, right? The actual times, those are great, but really what we're trying to figure out is what is the difference in the time between these two things, okay? And so we start with testing this just like we do any other hypothesis. We develop a hypothesis. Again, the null hypothesis is that the difference between these is zero. In essence, it really doesn't matter which service you choose. The alternative hypothesis here is that the difference between them is not zero, that there is a difference between them, okay? And the little d here denotes it's a good reminder that the match pair provides a difference in the data and that we are focused not on the individual delivery times in this case, but on the differences of those delivery times. Okay. The math works out like this. Our level of significance is specified at 0.05 or 95% confidence. The average difference is what we're interested in here. Okay, the 2.7 minutes. So again, how we found the average, we simply summed up all the differences and divided by the number of differences that we had. If we can ever find an average, we can always find a sample standard deviation. And so from sample standard deviation, we can get to a t distribution. Remember, a t distribution is different than our normal distribution. It has fatter tails, and we use this whenever we do not know a population standard deviation. So since we only have a sample standard deviation, we use our t distribution. Okay, and we get to a t value of 2.94. We can go to any table and look that up, and we can determine that a t-value of 2.94 with 9 degrees of freedom, and the p-value is between 0.02 and 0.01. This is a two-tailed test, so we would simply double that in the upper tails. And again, in essence, because the p-value is less than our alpha, we can reject the null hypothesis that there is no difference, and we can determine that there is a difference in the service time between these two companies. All right, so that's the p-value approach. Using the critical value approach leads to the exact same conclusion. We simply cannot tell by how much we can reject, just that we can reject the null hypothesis. And again, there we have it. Our t-distribution is commonly going to be used when we're comparing two samples together. Okay, if we're looking at two or more samples, we can use ANOVA, and ANOVA stands for analysis of variance, or I'll call it analysis of variation. And again, it's used for, this says three or more. It can be used for two or more, but normally we're going to see it with three or more population means. All right. And our goal here is to determine if there is a difference between any of the population averages. Okay. So the null hypothesis will always be that they are equal. And the alternative hypothesis will always be that they are not equal. Okay, that indicates that it is um, a two-tailed test for us. So if the null hypothesis is rejected, we can conclude that all the population means are different. Again, rejecting the null simply means that at least two of those population means are different. And we'll talk about how do we determine after that which of the means differ the most from each other. Okay. Some of the assumptions. One, each population, the response independent variable is normally distributed. The variance of the response variable, denoted as R sigma squared, is the same for all populations, and the observations must be independent, indicating that one observation is not affected by another observation. Some additional terms that we need to understand. A factor is going to be a variable that the experimenter has selected for an investigation. It's our independent variable, okay? The independent variable affects the dependent variable, right? It's typically a categorical predictor variable, and it may or may not indicate a cause and effect relationship with the response variable, and that's going to depend upon the study design and some analysis things, okay? The multiple factors, where there are two or more factors that define the experiment. The treatment is the level of factor. These are the groups. Experimental units we can think of as the observation. Completely randomized design is an experimental design in which the treatments are randomly assigned to the experimental units. And then our randomized block design, or two-way ANOVA, allows for the groups similar treatments. Okay, a randomized block experiment is an extension of a matched pair experiment. Okay, so don't confuse a two-way ANOVA, which is randomized block design, with a two-factor ANOVA, which sounds similar, but they are different. So a two-factor ANOVA is simply going to have more than one factor, more than one independent variable. So let's visually see how this looks. Here, our independent variables are the factors, right? We are looking for, here it's vitamin E and vitamin C are the factors that we have. And then each factor has different levels. Vitamin E has two factors. Vitamin C has three factors, 0, 250, and 500. Okay. Each factor has two or more levels. Combinations of the factor levels are called the treatments. So here we are vitamin C, 0 milligrams, vitamin E, 0 milligrams. That is treatment number 1. Vitamin C, 250, and vitamin E at 0. That is treatment number 2. And on we go. Okay. So in this hypothetical experiment, the researcher is studying the possible effects of vitamin C and vitamin E on health. There are two factors, right? The dosage of vitamin C and the dosage of vitamin E. The vitamin C has the three factors like we talked about. Vitamin E has the two factors, or the two levels, right? And the experiment has 6 treatments: treatment 1, treatment 2, treatment 3, and so on. The experimental units, these are going to be the recipients of the experimental treatments. And so the experimental units in an experiment could be anything. It could be people, plants, animals, or even inanimate objects, right? And then the dependent variable in the hypothetical experiment above, the researcher is looking for an effect of the vitamins on health. So the dependent variable in this experiment would be some measure of health. So that could be annual doctor bills, number of colds caught in a year, the number of days in a hospital. There's something that they're trying to measure the effect of this vitamin C and vitamin E level on. How does that actually affect the person, right? Do they feel better? Do they sleep better? Do they have less fevers? Things like that. And more as a review, just remember statistical studies can be classified as either experimental or observational. So again, an experimental study is going to have one or two factors controlled. We are measuring something. We are controlling how much of the vitamin C or vitamin E a person is getting. In an observational study, we're simply observing. We are looking at what's happening. We're noticing what people are doing, and we're looking at what those effects are without trying to control the environment in any way, shape, or form. Cause and effect relationships are easier to establish in experimental studies than observational studies, but a lot of times in statistics, we rarely say that just because things go together doesn't mean they cause each other. Okay. So, but an analysis of variation or analysis of variance, the ANOVA can be used for either one, for experimental or observational. So the basics of ANOVA are to determine the variance, and we're going to have two separate estimates, two independent estimates of variance. One is going to be understood as um, the error or the variance that happens between the treatments, and the other one is going to be within the treatment. So we're going to compare the mean square due to treatments and the mean square due to error. So one is between, which is our mean square treatments, and one is within. Um, and I'll show you this visually here in a second, but the ANOVA is typically used when dealing with, again, three or more, because again, we've got like a t-test for the two population comparison. And really what we want to be able to find here is we are comparing, just keep in mind, we're comparing the variances, and this is using the F-test. So we had our Z-score, we had our t-test, and now we're moving into our F-test. So let's take a look at a hypothetical experiment here. We've got an experimental design. We're looking at three different car waxes, right? And the observations that we have are on these five cars. So what we're doing is we're running these waxes through a car wash to determine when the wax starts to break down and deteriorate. So here on observation number one, it took 27 washes in a car wash before the wax started to break down. And then wax number two took 33, and wax number three took 29. Okay, and so what we're looking for here is we're looking for the variance that happens within each of these groups. So the variance within each of these groups, and we're comparing that to the variance that happens between each of these groups. Okay, and that will produce an F value for us. You'll see here on the next couple of slides how the ANOVA table is set up. But again, that's the basics of ANOVA is we are analyzing the variance, the analysis of variance, the analysis of variation that occurs within the groups versus between the groups. If there's more variation that is happening between the within the groups than between, then we know that we will have a smaller F value, and there's a good chance that there's not really a statistical difference between them. However, if we figure out that, wow, the variation that happens here is really small, but between them is really big, that's going to tell us, wow, there is a difference between these means. There is a statistical difference between these two types or three types of waxes. Okay. So here's our ANOVA table. Again, if you remember, our treatments are between and our error is within. So sum of squares treatments. The degrees of freedom is k minus 1. Again, we talked about degrees of freedom already, but in this case, k is the number of groups that we have. And for our degrees of freedom for our sum of squares error is going to be our nt minus k. Nt is the total number of n's that we have in the entire experiment. NT stands for total number of n's, and we're going to subtract that from the number of groups. At the end, our sum of squares total, when we add these up, the error, the difference between and the difference within, they'll have a sum of squares total. And then our degrees of freedom will also total. It'll be our NT minus 1. Just similar, very, very similar to our N minus 1, the NT, the total number of n's minus 1. From there, we subtract. We take our SSTR, our sum of squares treatments, divided by our degrees of freedom, and we take our sum of squares error divided by our degrees of freedom, and we get to our mean squares due to treatment and our mean squares due to error. We take mean squares treatment divided by mean square error, and that formula, that number we get, is our F value. And so if the F value is pretty big, something bigger than, say, like 5, all the way down. It depends on the degrees of freedom, of course, but if it's a big number, we know that there is a large difference that is going on between these groups that we've got. Okay. So again, our ANOVA table will be broken down into our sum of squares total will be the sum of squares due to treatment plus the sum of squares error. And here's the formula for that. This some new notation here. This X bar bar is our grand mean, our great grand mean, the mean of all means kind of concept, where we take the means from each of the groups and we find that average of the averages. Okay. Everything else here and here just simply says sum up all of the x's, right, for all the entire observations that we have, minus the grand mean, square that, add them all together, and we're going to get our SST, our sum of squares total. All right. And then again, our hypothesis for all of our ANOVA is simply that the null is that they are equal, and the alternative is that the populations are not equal. And the test statistic, very similar to the Z or the T, is our F, is our test statistic. The rejection rule, the p-value approach, critical value, the exact same concept follows through here. Our p-value, if p-value is less than our alpha or our level of significance, we're going to reject. If the p-value, the f-value is into the rejection region, we are going to also reject the null hypothesis. And again, we need these two different degrees of freedom in our numerator and denominator in order to look these up on the table. Again, probably not something you guys will need to do, but just wanted to make you aware of that. So once we've discovered that there is a difference, now we need to figure out where that difference might be. And so this slide kind of breaks down the three different ones, but we have the Fisher's least significant difference, the Bonferroni's adjustment, and the Tukey's multiple comparison method. Again, when we run an ANOVA test and we get a significant results, there is a difference, right? At least one of the groups tested differs from the other groups. We'll need to be able to figure out which of those groups is the difference. And ANOVA doesn't tell us that. So in order to address this, Fisher developed the least significant difference test, which is only used when we reject the null hypothesis as a result of our hypothesis test results. The least significant difference is going to calculate the smallest significance between two means as if a test had been run on only those two means, as opposed to like the entire group. This enables us to make a direct comparison between two means from two individual groups, and any difference larger than the least significant difference is considered a significant result. All right. Fisher is more likely than ANOVA to conclude that the difference exists in some of the population means, when in fact none of the means differ significantly. And so that's an issue we want to be aware of with Fisher's. And then the Bonferroni correction is used to reduce the chances of obtaining a false positive result or a type 1 error. Okay. To perform the Bonferroni correction, you divide the critical p-value or alpha by the number of comparisons being made. So for example, if we had 10 hypotheses we're going to be tested, the new critical p-value would be the alpha divided by 10, and then the statistical power of the study is then calculated based upon the modified p-value. Okay, and then Tukey's multiple comparison method is used to test differences in pairwise means, very similar to our least significant difference in that there is a critical number, the omega, that is used to compare all the means. All right, so again, ANOVA finds us, yes, there's a difference, we've rejected the null hypothesis, then we would further do one of these three methods in order to figure out where that difference lies. All right. I think it's best to kind of work one of the just an example problem here. This is going back to the wax, and so here's what we've got. We've got Auto Shine is considered marketing long-lasting car wax. Three different types of waxes, 1, 2, and 3, have been developed. In order to test the durability of the waxes, 5 new cars are going to be sent through the car wash. We're going to figure out where the wax is going to start showing signs of deteriorating. Okay. And so, in this case, the factor is going to be our car wax. The treatments that we are applying is going to be type 1, type 2, and type 3, different types of car wax. Experimental units are the cars, and the response variable is going to be the number of washes that it actually takes. That's what we're looking for. How long the response variable is going to be, how long does the wax actually hold up? All right. So again, here's our data set. We've got our waxes, the number of times we went through the car wash. Our sample mean is 29, 30.4, and 30. And then our sample variance is 2.5, 3.3, and 2.5. Again, some of you might say, listen, sample variances, yes, they differ. One's 29, one is 30. They're different from each other. Yes, but are they statistically significant? Are they different enough from each other that we wouldn't expect to have a difference by random chance? And that's what we're trying to prove out. Okay. So Our null hypothesis is always the same for ANOVA. They are equal. Our alternative hypothesis is that they are not equal to each other, where the population average for 1, 2, and 3 are the different waxes. Okay, so let's look at the calculations here real fast. We first need to come up with our grand mean, the x bar bar. So the way that we do that is we simply take the sample from 1, 2, and 3, we add them up, divide by 3, and we get a grand mean of 29.8. We need that grand mean to help us figure out our sum of squares due to treatment. And the formula is simply taking 5, which is our n, and we're going to take the 29, the average, minus the grand mean, square that. And we're going to do that for all of them. And we're going to add those up, and then we're going to divide by our degrees of freedom, right? So our 3 is the number of groups, k minus 1. So we have 3 groups minus 1. We get to a mean squares due to treatment of 2.6. So mean square error is a similar concept. We are looking at the variance for each of these, the 2.5, the 3.3, and the 2.5, and we are multiplying those by their n minus 1. So because each of the groups had 5 different, here, go back up here, each of the groups have 5 observations, we are taking that n minus 1, which is 4, times the variance. We get to 33.2. We simply take our NT, 5 times 3 is 15, minus K, the number of groups that we've got, and we get to 33.2 divided by 12 when we get to 2.77. Okay, so again, I'm not too concerned about the calculation process. Just know that we're going to divide our mean square treatments divided by our mean square error, and that's going to give us an F value. So in this case, when we do that, we get an F value for our critical approach of 3.89, and again, a p-value smaller than 0.05, we will determine that we need to reject the null hypothesis. When we figured out our numbers here, we only come up with an F value of 0.939. So the p-value is greater than 0.1, which is obviously greater than 0.05. We conclude that there's insufficient evidence that the mean washes, the 3 waxes, are not types are not all the same, right? In essence, we cannot reject the null hypothesis, and so now we know that all 3 waxes, they're about the same. What now do we do in business? Well, we simply look at, okay, what's the cost? Which one's easier to manufacture? How much can we fit in a bottle? Which one smells better? Whatever else we think is going to appeal to consumers, right? So that is what we will then base our determination on. Not necessarily that one is better than the other. They're all 3 about the same. Now, from a business perspective, which one makes the most sense? Okay. So here's how our table is ultimately laid out. Again, treatments is going to be the degrees of freedom for treatments are the groups minus 1. We had 3 groups minus 1. And our degrees of freedom between treatments is the observations, 15 minus 3, which is our 12. Okay. All right, a two-factor ANOVA. We have 2 independent variables in a two-way ANOVA are called our factors. There are 3 sets of hypotheses with a two-way ANOVA, right? The null hypothesis 1, the population means of the first factor are equal, and null hypothesis 2, the population means of the second factor are equal. Our alternative hypothesis is that there is no interaction between the 2 factors at all. The treatment groups are formed by making all possible combinations of the 2 factors. This is known as replicate. Okay. The idea here is that there are 2 variables or factors which affect the independent variable. Each factor will have 2 or more levels within it, and the degrees of freedom for each factor is 1 less than the number of the levels. So for example, if the first factor has 3 levels and the second factor has 2 levels, there will be 3 times 2 is 6 different treatment groups. All right. So suppose you want to determine, this is a good one, suppose you want to determine whether a brand of laundry detergent used the factor 1 independent variable, right? So laundry, the brand and the temperature are the 2 factors. Brand is factor 1, temperature is factor 2, affects the amount of dirt removed from your laundry. This is our dependent variable. So if you think about it, our dependent variable should be affected by whether we're using Tide or Gain or some other laundry detergent, and the temperature at which we wash our clothes. All right, so we want to understand that those two factors, those two independent variables, will depend or influence the outcome of our clothes, how clean they get. All right. So again, our null hypothesis, the amount of dirt removed does not depend upon the type of detergent, and the amount of dirt removed does not depend upon the temperature. And then the alternative hypothesis that we would use would simply be that yes, these do play a role in determining how much dirt actually comes off. Okay, so I hope that helps with ANOVA and understanding exactly how experimental design can be set up and some of the different factor levels for you.